Hello, this another exercise lesson video for exercise 19D for year 13 math students. We've done quite a lot of work recently on using vectors in mechanics questions. A bit of SUVAT, a bit of F equals MA, a bit of differentiation and integration when we have non-constant acceleration. But it's all up the time up till now it's been with 2 dimensions, and so this is slightly different in as much that we're switching now to 3 dimensions. So let's have a look anyway. Point A and B, this is a little starter for us. So point A and B have vectors, position vectors. A is 12 minus 7 and B is that. Find the midpoint. Oh right, you should remember this is how to find the midpoint of a vector. And it's very similar to coordinate geometry. So to find the midpoint of 2 vectors, you basically add the 2 vectors together and you half it. There you go. To find the position vector of M, that's that one, find the exact distance. Well, that sounds like Pythagoras to me. So will you do us a favour, please? Pause the video and have a go at those 2 questions. Right then, I'm hoping you've done that. If I was doing this position vector stuff, the M would equal, well, I'd add these together, that gives me 9. Add those together, it gives me minus 2, and I have to half it, so that sounds to me like, well, you could have 9 over 2, probably easiest, and minus 1. Okay, it's the position vector, so that's what we write. Technically, it's the position vector is called OM equals. I don't think it'll care about that. Find the exact distance from B to M. Well, so if you just draw a little picture, B is minus 3 and 5 up. There we go. There's B. And M is 4.5 across and 1 down. There's the M, and we want the distance from one to the other. And you can clearly see we're going to use Pythagoras. So what we need to do is obviously work out the difference between them. So it's this one and this one which I'm using. So from minus 3 to 4.5, I reckon that's 7.5 or 15 over 2, which I'm going to have to square. That's the 15 over 2 there going across. And going up, it goes from minus 1 up to 5, I reckon that's 6. So plus 6. And both these numbers have to be squared and then square rooted. And that's the distance. So hopefully you got the same as me. So doing it on my calculator now. And according to me, it is 9.60. Oh, it says the exact distance. So good job I didn't stop there. 3 root 41 over 2, according to my calculator anyway. So 3 root 41 over 2, that's right, and that's right. Okay, so up till now we've only looked at 2-dimensional problems, with the mechanics at least, and we've already seen how we can write using i's, j's and k's, a vector in 3 dimensions. But other than that, broadly everything stays the same. So I don't really want to go over that too much. What happens if we add a couple of vectors? Well, it's no real surprise. In 2 dimensions, if you add or take them away, well, this is obviously minus 2 and 5. If you do it in 3 dimensions, it's exactly the same. You just go 7. Adding this, so this is really 2 take away 1, which is 1, and that gives me minus 1. So no real surprises if you add and subtract vectors. Likewise, position vectors work in 3 dimensions just as well as they do in 2, and we had that rule that we will still apply. If you ever want to find a vector from one point to another, in this case A to B, you do the wrong one way down the first one, minus A plus B, or better written B minus A, and you just switch the letters around. Those rules still apply in 3 dimensions. Then let's do this question. It says CD. Express CD as a column vector, so that's easy enough. So CD, I will just do it the wrong way around. So I'll do D minus the C. So that's minus 1 minus 1 is minus 2. That's 2, and that's 2 take away 2 is 0. There you go. Let's be honest, that's not hard. Vector addition then, again, this is the same as before. If I was doing from what do I want? I want from A to C, it says. It says find A to C. So from A to C can be thought of as going from A to B, plus then going from B to C. As long as the middle letter is the same, then you can just join them up like that. pictorially, this is, I don't know what the picture looks like, by the way, I'm just making this up. But if I go from, that's the A, don't know why I put it there, and that's B, and then I go from B to C, I'm basically saying going from A to B and B to C is the same as just going directly over from A to C. That's all this is. So in terms of the picture, we've got it. In terms of the maths, it's just obvious. What is BC? That's 1, 1, 2. So just add them together then. Okay, fair enough. 2 minus 1 and 5. Again, not hard. 2 minus 1 and 5. Notice that's being written in I's, J's and K's. I've written it as a column vector, but it's the same thing. Another example then. It says write the following vectors in component form. Now if I want MP, how do I get from M to P? Well, I go from M to N, and then I go from N to P. So I think as a column vector, that's 3 minus 2 and 6, plus MP is 1, 1 minus 3. So that's fairly obviously 4 minus 1 and 3. What's P to M then? P to, oh, that's going the opposite way. I just realised MP, PM. Well, it's just the opposite of this. So rather than 4, it's minus 4. Notice I'm not even doing any maths, I'm just changing those numbers. This was 3, so now it's minus 3. I like that a lot. Easy peasy. PQ, well, that's going from there to there. So notice I go from P to N and then to M. Well, I can just do that. I can say, well, it's PM then, plus from M to Q. And luckily I have all this stuff. P to M I've already calculated. So minus 4, 1 minus 3. And I need MQ. MQ, they tell me, look at that, it's handy. They've even given it the right way. It's minus, be careful, look at that, that's a trick. I's, J's, K's, they've missed out the I. That must be a naught. Minus 2, 5. Nearly fell for that. And minus 4 or minus 1 and 2 seems to be the right answer. 4 minus 1, 3, yes. Minus 4, 1, minus 3. Minus 4, minus 1, 2. Perfect. All perfectly good. Now remember, the modulus is another name for the magnitude of a vector. Pythagoras, effectively. We see it loads. Here's my question. A and B have these position vectors. Well, first of all, we'll find AB. If I want to know the exact distance from A to B, we will find AB. And you always do B minus A. So I'm going to do 5, 2, 3 minus. Ooh, I keep on getting that recently. I think I might need to buy a new pen. But who knows? Minus 2 minus 1, 5. 3, 3 minus 2. Now, to find this distance AB, this is the magnitude. That's the posh way of writing it. Technically like that. But the lines around it mean the magnitude of A to B. And that equals the square root of 3 squared plus 3 squared. And ignore the minus, plus 2 squared. That's 9, that's 18, plus 4 is 22. It is root 22. Can I do anything with that? Well, only 2's and 11 go into that, so I think that's the answer. Root 22 is the answer. That says C. I don't know why it says C. That should have said magnitude of AB. There you go. There you go. That's the end of the lesson. 8 minutes gone, and we're sorted. Now, that implies exercise 19D isn't too tricky, but who knows? I'm just going to quickly look at the exercises now. And I just have looked at the exercises. It broadly is that. This is, I mentioned mechanics at the start. There is, I can see very little, if any, mechanics in that set of questions. So this may well be a kind of warm-up for mechanics questions which are coming up later on. I've also looked at 19E, exercise 19E, and that's also more to do with like pure maths rather than mechanics. So they've thrown it into this exercise, and it's the pure maths side of things rather than the mechanics. As I say, I suspect it's because we're going to need all this stuff in exercises on chapter 20 and chapter 21. But we'll wait and see what comes our way. All the best. Thank you very much.